Okay, so our class is now being recorded. I just start sharing my screen and okay, I think you should be able to see my screen now. Okay, just one more minute, second. I just need to open up my chat window. So okay, I just put in a I just put a test message on the chat just to get it working. Okay. So welcome to class number 8 of our course on network fundamentals for cloud. Give me a moment, guys. I think I've accidentally joined on two devices around. Just one second. Okay, I think we are now good. Just quick check. Can somebody just post something on the chat window? Just want to make sure. I see messages from Jyoti and Priyank, and Tanya, but they were earlier message. I just want to make sure after my test message. Yeah, thank you, Tanya. That works. Okay, so today thank you, Pani Bhushan. Class number 8 of our course on network fundamentals for cloud. And as I mentioned last time, what we discussed today is not part of your mid-semester syllabus. So our mid-semester syllabus is the entire set of topics that we've done for network fundamentals, and then the discussion we had around SDN and NFV, which is the enabling technologies topic. So today we'll start the topic of data center network, uh, and we'll take an overview of what exactly is the data center network, how does it differ from a communication network like the internet, and what does it mean from a networking standpoint? I mean, the difference in traffic pattern that we observe in a data center network, what it really implies from a networking standpoint. So that's a quick overview we will take today. So when we talk about, I mean, the course is titled Network Fundamentals for Cloud. And essentially, it's all about what we're going to discuss from here on is all about networks that are getting established in the cloud. So when we talk about networks in the cloud um, or cloud networking, okay, there are different subtopics that you will get exposed to. So one is you will build an understanding of how do we distinguish between a physical network versus a virtual network. And this is also something that we discussed when we talked about network virtualization in the last class. We noted that a physical network is a network that is created out of the physical infrastructure that exists in the network, including routers, switches, communication nodes. That's what creates a physical network. But on top of a physical network, I can use virtualization technology to create multiple virtual networks. And we saw the example of VLANs, virtual LANs, or virtual private networks, VPNs, as examples of these virtual networks. So when we talk about cloud networking, we will actually spend a considerable amount of time talking about the physical networks that make cloud networking possible, as well as the virtual networks that get established, which again can be called networks in the cloud, but they are virtual in nature. Okay. So to be precise, when we talk about the physical networks in the context of cloud computing, in the context of cloud, we will really be talking about what we call as data center networks. Okay. So I'll today talk about what we mean by a data center, what is a data center, and then what is it that a data center network is, why are we calling it a physical network that exists inside of a data center. But on top of a data center network, which itself is a physical network, a lot of virtual networks can be created, and these virtual networks are actually tenant specific networks. Okay, so a data center is typically owned by a data center owner. Okay? And the data center owner typically also is your cloud service provider. So if AWS or AWS or Azure Cloud or Google Cloud are the cloud service providers, then they also own their own physical infrastructure in the form of a data center. And all this physical infrastructure inside the data center is networked together using a physical network that is the data center. So first few classes from here on, 3 or 4 classes from here on, will be all about the physical networks that makes cloud networking possible. We'll be talking about different aspects of data center networks, the protocols used, the difference in the traffic patterns, the topology of these data center networks, and how do you connect multi-site data center networks, which eventually enable you to create multiple availability zones or provide you geographical redundancy. Okay, so 3-4 classes that we are going to talk about, it's all going to be about the physical underlying networks that enable cloud networking, which is about data center network. And then we will move a layer above to talk about the virtual networks that get established over this data center network, which is what a tenant has when he or she creates a VPC, a virtual private cloud network on AWS. It's a virtual tenant specific network that gets established. So we'll follow up the discussion in the subsequent classes, the discussion about how do virtual networks get formed on top of a data center network, what are the protocols involved there, how is routing of traffic happening in these virtual networks, so on and so forth. Okay. In this context, it's also important to understand the terminology underlay versus overlay. So in general, the term underlay is used to denote any network that lies underneath, and the term overlay is used to denote a network that lies on top, over. Okay? And therefore, when we look at physical networks in the form of data center networks and virtual networks in the form of those tenant-specific virtual private cloud networks, you can say that these tenant-specific VPCs that are getting established are actually overlay networks which are set up on top of an underlay network, which is the data center. Okay, so that's another term that you will get exposed to quite much in these next few classes. We will use these terms: physical cloud network, virtual cloud network. The physical cloud network is actually the data center network. The virtual cloud network is actually the tenant specific VPCs. And we will also call them as the underlay network, denoting the data center network, or the overlay network, the one which sits top of this underlay network, which essentially we will talk as the tenant specific. The third thing that you will see, we will talk about both in the context of physical data center networks and virtual tenant specific VPCs, is the concept of intra networks and inter networks. So we will see that it's possible to have a single data center network and multiple VPCs set up on top of that data center. But it's also possible to have multiple data centers which are networked together to form a multi-site data center network. So when I say multi-site, we are basically emphasizing more on the data centers. We are saying there are multiple sites for the data center. There's data center 1 in Bangalore, there's data center 2 in Hyderabad, there's data center 3 in Delhi NCR. All of them belong to the same owner, and they are to network together to create a multi-site data center. And the networking that enables this is actually creating a set of networks that are inter data centers, across data centers. So that is another thing we will be covering. How do you have multi-site data center networks? Is it possible to communicate across multiple VPCs? So when you communicate between VMs within a VPC, it's intra-VPC communication. But is it even possible to go outside of the VPC to an external network, even for that matter, the internet? And that is inter-VPC or outside the VPC communication. So all these aspects of networking is what we will cover over the next many classes when we are going to focus our discussion on cloud networking, or all the different forms of networks that we can see in the context of cloud computing. Okay, and in all of this discussion, you will realize that the reason we spent 5 classes or 6 classes on building a good understanding of network fundamentals was because those same fundamentals get reused most often than not in the cloud networks as well. Okay, so this is what we will talk about. Okay, so we'll start, as I said, with data center networks, which, as I just explained, study the specific aspect of cloud networking, which is the physical. Okay, so this is where we are in our course. Remember the first class we had, contact session 1. I had talked about our course structure. I had said we will go about in 5 steps, gathering a good understanding of networking principles used in the cloud. We will start with general network fundamentals, which we are going to anyway keep using throughout. That's what we did first. Then we moved to enabling technologies, SDN, NFV. We gathered an understanding of that. This is where we are in our course structure. Okay? 3 or 4 classes, we are all going to be talking about data center networks, the physical network that realizes the virtual cloud network. So these are the underlay networks. And then we will talk about the overlay cloud networks, which are the virtual cloud networks or VPCs that are formed on top of the data center. And we'll end our discussion by talking about, because these VPCs or virtual cloud networks are going to be used using network virtualization and also network function virtualization. And this was a question in the last class. Isn't the performance getting or taking a hit? Because these network, when we are using network function virtualization, we are actually relying on what? We are relying on VNFs, virtual network functions, like V routers, V switches, to create a virtual overlay network for a tenant. Is the performance of the V routers or V switches at the same level as a physical router and a physical switch? No, we know that. But then what can be done to improve the performance of these VNFs? That's where we'll talk about network performance improvement ideas. And towards the end of our course, we will talk about network security. Another topic which I have not mentioned here, but we will cover is also network monitoring. Okay, so performance cannot be measured unless you have effective monitoring tech methods in place. So network monitoring, network performance, network security. These are the last 3 topics that we will cover in our course. So this is just to give you a revise where we are currently in our course. This is where we are currently, right in the midway of our course. Okay, so let's start by trying to understand the role of data center networking in enabling cloud-driven networks. So what is the role of a data center? First, in realizing what we call as the cloud. When we say my services run on the cloud, or my server is sitting on the cloud, what is the cloud? Where is the cloud? And what is the role of the data center in realizing whatever we are calling this cloud? So essentially, the data center is nothing but it's a collection of all the physical infrastructure all those ingredients that you need to create a cloud computing environment. And what are these ingredients that I need to create cloud computing environment? These ingredients are compute servers of different capacities, different types. Okay? So I need compute engines or computing machines that are ingredients for cloud. Then there are storage. I need storage of different types, different capacities. And the network is an essential component of the cloud because it is what is connecting these ingredients together. Because if there was only compute and storage and no network, how would I even reach out to these compute engines or these storage machines without a network connecting these ingredients together? So a course like what we are doing, Network Fundamentals for Cloud, while you might believe that you're not networking engineers, you're not somebody who's going to work on networking primary, but understanding computer networks and specifically in the course in an MTech on cloud computing, fundamentals of networking for cloud is essential for you to be able to realize or build any cloud enabled solution. Because essentially it's the networking which is connecting all these solutions or components together. Okay? That's why it's one of your core courses, and that's why we are studying this course. Okay, so what is the data center network? It's the network that is connecting all the assets, server machines, storage machines together inside a data center. Okay, so I'll just use 2 or 3 minutes. It's not a very long video. It's just a 2-3 minute video that I'll play. Okay? I want you to watch it. It's a video about Google's data center network. They'll very quickly in 3 or 4 minutes talk briefly about what a data center network is all about, and it'll give you a perspective even before we move ahead. Okay. Sorry, I forgot to share my audio, so I'll have to stop sharing once and restart sharing. Just bear with me for a minute. I've stopped sharing. I'm going to start sharing again, but this time with the audio enabled. Okay. So the reason is when I play this YouTube video, you should be able to listen to the audio. Okay. So that's the okay. How, yeah, that should.
Whenever you use a Google product, you're connecting to one of our data centers around the world. Let's take a look and
Quick check. Is the audio coming fine for the video? Are you able to listen to the audio? Sorry, I don't see anything on the chat. For the brief moment that I ran the audio, were you the YouTube video? Were you able to listen to the audio? No. Ah, thank you, Tanya. Thank you, everyone. Yes. Okay. Let me restart it. Yeah. So I'm playing it now.
Whenever you use a Google product, you're connecting to one of our data centers around the world. Let's take a look inside and see how they work. Google employees work here, keeping the data center up and running 24 hours a day. The networking room is the first stop on our data center floor. The equipment here routes requests to the right servers in the next room. These computers also allow our data centers to communicate with one another globally. On the server floor, powerful computers handle everything from billions of searches to hosting YouTube videos and protecting your email against viruses. We've custom designed these servers to be compact and energy efficient. To ensure you have access to your data whenever you need it, we keep each piece of data stored on at least 2 servers. We store another copy of the most important data on digital tapes. When a hard drive breaks, we erase all of its content. Then, for extra security, we destroy it with our disk crusher. The machines in our data centers are always working. Cooling towers like these pipe in water to cool them down and keep them running. When the water heats up, we pump it back outside where it evaporates. Now that you've had a glimpse, walk inside yourself. Explore a Google data center with Street View. Whenever you
Okay, so that was the video that I wanted you to see, just to get a perspective of what do we mean when we say data center. Hmm? So what is it that we saw very quickly in these 2-3 minutes of video? We saw a data center, right? We saw the Google data center, which, as I said, is whenever you're using a Google product like YouTube or Google search, you're actually hitting some server in the Google's data center. That's the one who's going to provide you. So yes, they talked about a separate area which is the seating area. So this is where the people sit and they work. And they keep the data center operational 24/7. That's what they said. So what was the first thing they talked about? The most important thing about the data center, apart from the seating area, they mentioned something called the networking. So two things that were said about the networking room, two key functions they noted about the networking room. Does anybody remember what was said in the video? What does the networking room do? Two things that the networking room is doing. So who made a note of what they said about the networking room? Meanwhile, I'll just continue. So while you type, and the third thing they said was the server room, right? Which, of course, once we see a Google data center, it gives you a, a view into the volume of servers that exist in the server room. So yeah, thank you, Nikhilesh. Nikhilesh saying routing. Yes, that's right. So network room is actually handling all the traffic, but they said two types of traffic that they mentioned. One, they mentioned that the role of the networking room is to make sure that the data center, which, if you remember in all our previous discussions when we were talking about the internet structure, what did we call the data center to be, or the data center network to be? We called it an example of an access network. Okay? So just like an enterprise network is an access network for all machines or server machines sitting inside an enterprise, just like a Wi-Fi network at my home is like an access network for all machines at my home to enable access to the internet. What does a data center network do? It's like an access network that can provide access to and from all these servers in the server room to the rest of the internet. Okay, so if I draw the internet like this cloud, then the networking room is enabling connecting this data center network, which is like any other access network, to the rest of the internet. So traffic to and from the data center passes through the networking room. It's the responsibility of the network devices in the networking room to connect the data center to the rest of the internet. And that is the only way why me, somebody sitting at home over here with my laptop, I am able to open a YouTube video just like we did right now, and via the internet go and I access some YouTube server in the server room, and I'm able to access that video because I get routed via the internet, via the networking room until I hit a YouTube server which is hosting this video and serving me. Okay? So that's one of the functions of the network. But then what is the other view we saw inside the server room? We saw a phenomenally high number of physical servers. I mean, it's humongous. When you see it, it's an eye opener. You see such a large warehouse, but that warehouse is not storing any other commodity. It's storing servers as a commodity. These are commodity servers, which are put into racks. You saw how they said these are very efficiently designed servers that can, when they slided it inside the rack and just connected it to the backplane, right? So that its part becomes a part of the network and it starts to draw power from the rack. Okay? They are elegantly designed to be fitting into the rack shelves, connect to the back networking backplane of the rack server, drawing power from the rack machine, and then they are energy efficient is what they said, right? So that's where the server room is. Now these servers need to communicate amongst themselves. Why do these servers need to talk amongst themselves? Because just now we said, while this may be the data center network, on top of the data center, we will have tenant-specific virtual networks. And what is a tenant-specific virtual network? Even before we reach that topic, very quickly, we understand that just like when we talked about virtualization, I said, if there are two servers in the server room, both these servers could be running a virtualization layer in the form of a hypervisor, and I could be running multiple VMs on top of each of these physical servers. So this is physical server S1, this is physical server S2. Both are part of the server. On top, I have VM V1 to V4 running on server 1 and VMs V5 to V8 running on server 2. Let's say for one tenant, V1, V4, and V8 belong to one tenant. So when I create a virtual network for this tenant, I'm actually creating a virtual network that connects machines V1, V4, and V8 together via some form of a virtual network function. I'm actually creating a VPC, a virtual private cloud. But in reality, we know that these VMs are not all on the same server. Between V1 and V4, we can use what we talked earlier as internal network virtualization, and we can connect them together via a VNF that sits inside the hypervisor. But what about V8, which sits on a different server? Traffic will have to be physically routed over the data center network to reach server 2 and therefore to reach V8. So who's doing this? This data center network is part of the networking room. The networking room is also connecting servers like S1 and S2 together so that communication between physical servers, which is a consequence of VMs talking amongst each other, also becomes possible. Now, this is not just server to server communication. The last thing they said was about storage. So they have storage devices, including tape device drives. Tape drives are the redundant storage that they said, right? But the disks are the storage devices that they use for connecting to these servers. So if a server has to connect to a storage area, a storage disk, who provides that networking? Once again, the networking room. So the networking room or the data center network, as we call it, is the network which is connecting all these other assets, the servers, the storage, together within the data set. Right? So it plays a very essential role in realizing the cloud environment. Right? So that's a quick overview of what is a data center network. Now, when you go through your textbooks, I mean, I've prescribed 2 textbooks for this part of our course, right, on data center networking. You will see that sometimes in some places the textbook also use a term cloud data center. Okay, don't be confused with what they mean by it. Right? Cloud data center network. They're basically referring to a new type of data center that is based on the cloud computing architecture. Right? So they're basically talking about a virtualized data center. So when they say a cloud data center, so just like we said, a data center is actually, when we just say data center, we're actually talking about a physical data center with all the physical infrastructure. But when somebody says a cloud data center or a cloud data center network, a cloud data center is a special type of a data center where the data center infrastructure is fully virtualized. Okay, so we are talking about a set of virtualized servers, virtualized storage, virtualized network, creating a cloud data center. Okay, so data center network is what we are going to focus on. Okay? The physical data center is what we are going to talk about. When somebody uses this term cloud data center, he's more talking about a data center that is set up using virtualized devices. Okay, an example of a cloud data center is something that we will see later when we look at a case study of a content delivery network. Right? A content delivery network like YouTube, or what solutions like service providers like Akamai enable. They actually help you create a content delivery network. They often use cloud data centers to create their content delivery environment. We'll look at that example later at some point in time, but right now in all our discussion that we will have for the next 3 or 4 classes, this is what we are going to talk about, data center network, not this part. Okay, we're not talking about virtualized data centers. Okay, so when we talk about the data center network, the first point to discuss is, since we've done so much of discussion around the internet, taking the internet as a case study for us to understand all the other networking fundamentals like switching, routing, congestion, flow control, we use the internet as a case study because the internet is the most commonly used communication network that all of us use. That's one. Two, it's the largest network, public network known to date, and it still works. So any networking principles or foundations that make the internet work are worthwhile to even make a data center network work. Correct? Right, Pradeep. What you said is also an example of a content delivery network. So Amazon CloudFront enables creation of content delivery network. Right. So we'll talk about that later. Another 3 or 4 classes later down the line, we'll talk about these things. But right now, we are talking about the physical data center and the network that connects this physical data center. Now, if we have to understand how a network evolves and therefore also understand how the data center network topology has evolved, it's important to understand a concept that in the networking fraternity is often termed as the application network dance. Okay, why dance? So you would have seen in movies, or maybe you've done it yourself. If you've gone to a ball dance, okay, a pair of a pair or a couple will be dancing, okay, together, and you believe that the two of them are dancing as a pair. But people who are familiar with a ball dance know that in two people who are participating in a ball dance, it's actually one of the partners who's called the leading partner. He's the one who's leading the dance. And then the other one is following the leader. But they are doing it so seamlessly and elegantly that you believe they're dancing as a pair. Okay? So the same analogy holds true in networks as well. And here, the two partners who are part of that dance, the ones who are doing that tango, is actually the application layer, or this all the applications that we use, and the underlying network which makes these applications enabled, network enabled. Okay? So in modern era, all the network applications that we talked about, they all network applications. So in a way, we are saying these applications are dependent on the underlying network to be working because they're networked applications. So they are the two partners in a dance, and they're actually dancing. Right? Okay, the first part of this slide is just a reason because I'm sure you would be feeling, why am I telling you this story? It's actually a story. Right? It's like a story. But then this writer of Canadian descent, this guy, Charles Flint, he said, once upon a time, there was what there was. And if nothing would have happened, we would not have a story to tell. That holds very, very true for the application network dance. Okay? Because once upon a time, there was what there was. And this there was actually the internet. It existed as a fabulous network that connected the whole globe together, the world together. And that was there. It was there always. Right? We covered about the internet and the salient features of the internet in our 5-6 classes of introductory classes in this course. But if nothing more would have happened, we wouldn't be having 10 more classes of this course talking about what is there more to talk about. Things evolved. The internet continues to evolve. Networks continue to evolve around the internet. So there is a story to tell. And what is this story? This story is about the distributed applications or the networked applications which are continuously in dance with the network. And contrary to what you might believe, you might think the network is because the network is the one which is providing the service to an application, the network should be the leading partner. That's not the case. In this dance between the application and the network, it's actually the application which is the leading partner. The network is following the application. Okay. So when we talk about data center networks and we talk about data center network topologies, or even before we get to topology, when we talk about the nature of the traffic, network traffic that a data center observes, it's because of the application. The application is leading. The application is what is evolving. It's becoming more and more complex. Applications are becoming more and more complex. They are the ones which are leading. The networks are forced to adapt. They are forced to follow. They are forced to change their topology. They are forced to bring in new protocols for communication because that is what the modern applications require. Okay. So the story of the modern data center that we will talk about in the next 3 or 4 classes, it actually begins now from this class onwards. And in timeline, it actually began when people thought the internet was a perfect example of a network topology, and the protocols which run in the internet were a perfect example of the protocols that should be followed in any kind of a network. Because if a set of protocols can keep a huge network like the internet operational, then why not smaller networks like our enterprise network or BITS Pilani's institutional academic network? Why not those? It could work for everybody. But that was a misconception. Because the story of the data center begins when this network, which was designed with the internet as the ideology, this network was actually caught flat-footed in the dance when the application started to dance to a very different tune. And the network wasn't even prepared to follow or understand this tune. So all this while, when we talk about the next 3-4 classes, we'll actually are going to see how the application started dancing to a different tune and why the network had to evolve, because it was just not ready. It was caught flat-footed when applications started to just evolve into a kind of application that the network just could not support. Okay. So if we look at the evolution of the applications in general through history, so we are basically looking at the application history. We know that when the computers were first born, there was no internet. Computers were monolithic standalone devices built to assist a human. Something that I could not do on my own. I used a computing machine to do it for me. I used it as a piece of storage. I would store all information digitally in my computer more than maintaining physical copies. I would use the computational power of my computer to solve algorithms, which I did not want to tax my brain. So they were monolithic, isolated machines, not connected to a network. And therefore, any applications that were running on those computing machines were also monolithic applications. When we say monolithic, they were complete in their own sense. They did not have to talk to anybody else. Neither did they have to talk to anybody else, nor were they equipped to talk to anybody else, because these computers, they were standalone machines. Okay? But as the internet came in, what happened? These machines started seeing the benefit of getting connected together over what we now know as the internet. But it started as a small network, or the DARPANET or the ARPANET, which was a network set up for two purposes: educational purposes, EduNet, and defense purposes, called the DARPANET. So people saw that if I can harness the collective power of multiple machines together by connecting them over an internet, by connecting them over the network. And this is not the internet. The internet evolved when the World Wide Web came in, WWW came in. But this was just a network of machines put together to harness the collective power of the individual monolithic machines. Now, when this network got formed, monolithic applications evolved because a single application sitting on a single machine could only achieve as much. But when I wanted to harness the power of multiple machines together, I had to split up this application into multiple components so that the application had instances sitting on all of these machines together and they were talking to each other. So we basically are now looking at what we are calling as distributed applications. The simplest form of distributed applications that evolved first as the World Wide Web or the internet evolved is called the client server architecture. Okay? So the first internet generation that came out was called the internet of content. Okay? We had a lot of content across these machines together, but how do I use that content? How do I even discover that content? I need a web browser. The first web browser was Netscape, which helped people discover content available over the internet. World Wide Web was created as a services architecture on top of the network to create an internet of content. And to enable this internet of content, any machine which wanted to fetch this content would act as a client. The source of the content would act as a server. The client would connect to a server and fetch the data from the server. So client server environments evolved. The local area network became a reality. Okay? So applications evolved from monolithic applications to what? Client server based applications. We also sometimes commonly call them as web-based application because they follow the client-server paradigm. Right? It basically arose because of the web-based application design. Right? But then web applications realized that as the load on the servers continue to grow, so it's no longer one client anymore connecting to a one server, but there are now so many clients that have come up and they're trying to connect to the server to fetch this content. And not only that, by then, the World Wide Web had actually evolved to what we call as WWW Generation 2. It's also called Web 2.0. Right? This characterizes the emergence of service-oriented architectures over the internet. And this generation, which we also called as the second generation of the internet, it's also called the internet. No longer did we call it the internet of content, we called it the internet of services. Why? Because services like what we are using right now, Teams, it's an e-productivity application. Or e-commerce applications like the Amazon Marketplace, they came up. So servers started offering services and these clients were users of those services and they were in the hundreds or thousands. So a single server could no longer handle so many clients. So what happened? A new architecture for web-based applications emerged where the servers behind were split into multiple backend servers together handling the load in what we call as a load balancing configuration. Okay? So this is what we have in web applications today. You have so many clients. All of these PCs that you see are all clients connected not just over the local area network, but now globally over the internet. Okay? So it's not just within one network that you have a client server architecture. You have across the internet clients and servers and now these servers are the ones we are talking of in data center who are sitting and providing these services to global clients. So server architectures evolved to more distributed servers. So not only are we talking about distributed applications, distributed servers, which are sitting on different physical machines and implementing the three-tier web architecture. What is the three-tier web architecture? People familiar with web application design, they know that the HTTP protocol which we use over the internet, terminates on the web layer. It's called the web tier. Okay. This is typically implemented by our web servers like Tomcat servers and so on. And then the business logic sits on this second tier, which is what we call as the application tier. This is where the business logic is. So HTTP protocols terminate on the web tier. Then the HTTP part of your URL is shunted off. The rest of the URL is actually what is passed to the application tier. The application tier often to handle this web request needs some data, and that is where the third tier comes in, which we call as the data tier. So even a backend server application got split into multiple layers: the web tier, the application tier, the data tier, and there were multiple such servers with their 3-layer or 3-tier architectures running across different physical servers, right, in a load balance configuration. And today, even this has become an outdated architecture, right? Because now we know that even within the application tier, for example, the business logic could be very, very complicated. I cannot have one application tier as a monolithic process handling the entire application logic. Think of Amazon server, the Amazon marketplace. There are so many functions. When you first subscribe to the Amazon service, what are you doing? You are registering for the service. Once you registered, then you log into the service. Then when you after you log in, you go through the accessing the marketplace business. Once you purchase products, put it in the cart, you go through a checkout process. So each of these processes are independent, individual processes that are huge in their own sense. So what do we have today on the cloud environment? We have an application architecture that runs on the cloud, which we call a microservices architecture. Okay. So what is this microservice architecture today? We have further split the application tier into microservices, with each service playing an independent function. So I can say I have a registration function, which is dealing with new user registration. I have a login service, which handles the authentication part when the user first tries to log into the marketplace service. After login, he's able to access the marketplace. So let me call it just the marketplace service, where he's actually browsing through the marketplace and putting products in the cart. And then he's going to make a purchase. So there's the checkout process, where the interface with third-party banking applications and all also comes in. Right? So each of these is an individual service running independently on multiple machines, depending upon how much load does each machine have to handle. Each service have to handle. When you look at a registration service, it has lesser load because it's only once that a new subscriber will come and register himself. But login service has more load than registration service, because every time even as a registered subscriber, every time I log into the marketplace, I will go through the login service. The marketplace service and the checkout service will see much more traffic, consumer traffic, client traffic, compared to even the login service. Why? Because each time I shop, there'll be traffic coming to these services. So we've now come to realize that even the application tier doesn't get the same type of load. Different services within the application tier, like the registration, login, marketplace, or checkout service, each service has different traffic profile, different load requirements. So for each service, I need to run multiple instances of that service. Maybe for the registration service, I'll run only one instance. For login, I can run 2 instances. Marketplace service, I'm running 100 instances, and checkout also I'm running 100 instances, depending upon my workload. So this is where the microservices architecture comes in, and that's how the applications have evolved. Now, I'm not going to teach you application evolution, but I know you all are familiar. Being in the IT space, you've heard these terms. You've seen this evolution of application from monolithic to client server to web-based applications to microservices architecture. Okay? Now, why am I telling you this story? Is because when you look at the networks, and I said the application and the network are actually in dance together. When there was only that monolithic application, there was no need for networking. So either the networks did not exist, or even if the network existed, there was limited needs for the network. But as soon as this client server architecture came in, the concept of local area network came in, the TCP IP protocol stack came into existence. We needed standardized ways of communicating over the network between these machines. So the TCP IP protocol stack came. Designed based on the OSI reference model, which we discussed earlier. It's a practical communication stack used in the IP-based network for communication between machines. So this is what comes in. You have an evolution of the network. And then as the network further evolves to web-based applications and you want to solve these single point of failures and handle the multiple workloads, you have network virtualization coming in, multiple VMs running, different server instances, load balancing coming in as into picture. So the network evolved. Today, when we talk about microservices, we are talking about disaggregated servers sitting across multiple different virtual server machines across a data center. And this requires its own form of networking, which is driven by this more modern disaggregated server or microservice architecture, or what we also commonly know it as a cluster-based application architecture. Okay, so we no longer call it a distributed architecture because that's something we actually a term that we started using here. We said this is a distributed architecture. The server at the website, it's split into multiple tiers, and there are multiple instances of those tiers running across servers. It's a distributed architecture. But modern microservices based applications, we are talking about a cluster based application architecture. We have a cluster of nodes, whether physical nodes or virtual machines, virtual nodes. They are running microservices and multiple instances of the microservices as a cluster of applications. So architectures like MapReduce, where a single request, like a web search. Today, if I do a Google search, I search for some keywords. That web search comes to a central engine called the map engine. Right? And to make my search work very, very fast, I split that search request into multiple parts, giving that request to multiple servers to work on it in parallel. So it's basically using more parallel computing. Each of them uses a subset of the database to search for the keyword, so that in parallel, I can pass through multiple individual data sets. So each of these servers, they have actually taken a reduced problem, not the old original problem, but each of them have taken a reduced problem and they're solving it where? On a reduced data set. So the likelihood that they'll be able to solve it faster because they have a reduced problem on working on a reduced data set is much more likely, right? So they'll take reduced time to solve this in smaller problem. Now, when they solve this in the smaller problem, they solve it and they send it back to the central node. Okay? And what does the central node do? It consolidates all the results together as if it was the one which was searching for those that phrase in all these data sets, consolidates it, sends it back to the client. What is the net result? Google web search works much faster than what it used to earlier. Okay, but what does it require at the back end? What is this? This is a cluster-based architecture. I have a cluster of servers which are trying to solve a problem rather than one server doing that. Okay. And when this whole cluster of machines are together trying to solve the problem, they are doing what? What is the communication called over here? They are doing server to server communication. The map server is also a server machine. The client sits somewhere over here. I am the client who's triggering this web search. This guy receiving the request is a server machine, call it the map server. And then each of these reduced servers are also servers. Okay? So what do we have inside a cluster-based architecture? We have a lot more of server-server communication. Okay? So the original architecture that was there in local area networks was more of client-server communication. But when we look at modern microservices architecture or cluster-based application architecture, we are talking about a lot more server-server traffic, server-server communication. Okay, and that is the story that we are going to talk about when we look at data center network. We are going to look at what has how this application evolution has caused from a networking standpoint an historic shift from a predominant client server traffic based network to a predominant server server traffic based data center network. Okay, that is what we are going to talk about. First, when we look at a data center network, its traffic pattern, its traffic profile. What kind of traffic comes inside a data center? What kind of traffic gets exchanged within a data center? And what is the percentage of either of them? Percentage of traffic that is incoming into the data center from the outside internet, percentage of traffic within the data center, that is the server-server traffic. Okay? That is what we are going to first try to understand the nature of the data center net. Okay. So if we look at a closer, if we come back, I mean, this is the diagram that I had shown you when we talked about the internet structure. We had said it's a network of networks. And one of the networks we had in this diagram neatly hidden away was this data center net, which is what now we are blowing up and going to be focused on. It was part of the internet. It was always part of the internet. Just like an enterprise network has always been a part of the internet, my home network is part of the internet, the mobile network is a part of the internet. A data center network is also an access network, which is an access network to the rest of the internet. It's part of the internet structure. So when we talked about the edge devices, we talked about client machines, which were sitting on edge nodes. But we also were talking about the server machines, which we also said were at the edge of the internet. And that point in time, we made the statement that most of the time your server machines are actually hosted or kept in some data centers. Even before this cloud computing came in, the concept of data center was still there. So if Google, even before Google Cloud became popular, if Google was to have required to implement its own services, provide its own services, it required servers. And all those servers were inside a large warehouse, which was called the data center. So the data center was always the location where all these servers resided, and they were always on the edge of the internet. Now, when we talk about the data center network, as I said, the first thing for us is to understand, even before we go into depth about the topology or the evolution of the data center network itself, it's important to understand the traffic that comes into the data center network. On one side, we are looking at traffic that originates from client machines. Think of this laptop as a client or this laptop as another client sitting in a home network, connected via an ISP to an Amazon server sitting in the data center. This guy connected via the mobile network and then a global or national ISP and then reaching the same Amazon server. Hmm. So this is what is the client server traffic. A client is sending some traffic to the server. But what we are going to go look at now, so from the internet perspective, we were always looking at this client server traffic. So when you look at this core of the internet, the backbone of the internet, which is the combination of your tier one ISPs, internet service providers, or global national ISPs. That's the core or the backbone of the internet. For designing the backbone of the internet, we were more interested in the client server traffic pattern because that was the predominant traffic pattern in the backbone of the internet from one client to one server sitting in the data center. But now what we will do is we'll blow up this data center network and we'll say, okay, there's a client request that came in inside the data center to a server. But what is the server architecture? It's no longer a single server. It's a cluster of servers following some kind of a map reduce pattern, architectural pattern. So what is the volume of this server traffic that the data center network sees is what we are first going to focus on. Okay. So before I go ahead and talk about what many common data center networks observe, let me, since it's a 1 hour boundary at this point, I think we have got a good introduction to data center network. Let's take a 5 minute break. 11:32 by my watch. We'll come back sharp at 11:37. Okay, take a 5 minutes break and we'll continue. Okay, I think break time over, so we should start. Right. So the first case study that I'm going to talk about from a data center network perspective, which gives an insight into the type of traffic that a data center network sees, is the Facebook case study. And this case study is actually coming from a paper which I'll share with you later for extra studying, maybe after your mid-semester break, because a mid-semester exam, because right now you have a lot more to worry about. But after the mid-semester exam, I'll probably request you to read this case study. It's a good paper that talks about the Facebook data center network. Okay? So sometime after mid-sem, I'll ask you to read this. It's called the paper is titled Introducing Data Center Fabric, the Next Generation Facebook Data Center Network, Engineering at Meta. So for now, I'll just highlight one paragraph out of that entire article that I want you to focus on. Read this one paragraph for some time. Take some time, read it. Everybody should read it. Okay, everybody read it. So what is the first part of the paragraph that they're talking about? They're talking about what the story I just told you before we got into it. I talked to you about a application network dance story. Exactly what they're saying. Facebook's network infrastructure needs to constantly scale and evolve, rapidly adapting to our application needs. Who's leading the dance? Application. Who's following or adapting? The network. So that's the network application dance that I talked about. Okay. What's the second part of the statement that they're talking about? They're talking about the client server traffic. They are calling it, in Facebook terminology, machine to user traffic instead of calling it client server. But this is the traffic that comes to Facebook servers from the internet. People like you and me who access the Facebook server, we generate this traffic towards the Facebook server. Now they say that this traffic, which is client server traffic, is large and it's ever increasing. That's expected because there are more and more people who are becoming Facebook subscribers. And Facebook itself is coming up with new products and services for instant messaging and so on and so forth. So the traffic is growing. The important thing is what they say over here. However, this type of traffic is only the tip of the iceberg. It's only a small fraction of the total traffic. What happens inside the Facebook data centers? What we called as the server to server traffic, they're calling it the machine to machine traffic. It is several orders of magnitude larger than what goes out or comes in from the internet. Okay, so that's what Facebook has to say about it. Now, why is it that this is the kind of traffic patterns that data center owners like Facebook or Meta are seeing? Because of the applications. That's what they said. As our applications evolve and grow and scale, our network infrastructure has to keep pace with it. So the fact is that more and more DCN applications are becoming cluster-based applications. We are dealing with a class of applications that includes scientific computing, financial analysis, data analysis, data warehousing. What are these? If today an organization like Tower Research focuses on building quantitative trading algorithms, and by the way, they pay you by crores of rupees an annum. Why? Because they make money in that order of magnitude. But why are they able to make that kind of money? Because they're trading on the stock market using an extensive amount of data analysis that they're doing, which coupled with quantitative algorithms is actually giving them a very good view on the financial markets, financial analysis. But what do these kind of applications require? Huge amount of data that needs to be stored in data warehouses, extensive amount of data analysis, complicated quantitative algorithms that have to run on top of that data. Okay. So what kind of an architecture of applications are we looking at? A cluster-based application architecture. So where is the principal bottleneck going to come in when we talk about such large-scale clusters which are implementing such complex applications? The bottleneck that we are going to observe in such large-scale clusters is often going to be observed in the bandwidth that exists between the nodes within that cluster. So what we are calling at the inter-node communication bandwidth. That is where the principal bottleneck is likely to exist. Okay. So MapReduce, which I talked about earlier, is one of the examples of such cluster-based applications where you are actually doing a lot of data processing. A lot of data shuffling is happening. So every reduced part, so quantitative algorithm will work on a lot of data, but you can split that data into multiple subcompo parts. This can be a distributed algorithm. Every instance of the algorithm can work on a part of the data and then provide its outputs back to the map phase, where the map phase can actually merge all the out data and provide a consolidated answer. MapReduce is one architecture in this cluster-based application. There are other examples of cluster-based applications which run on cluster-based file systems. They require a lot of internode communication because there's a lot of, this is a cluster-based file system. So it's like a distributed file system. So there are going to be a lot of distributed input-output operations that are going to happen over the nodes in the cluster. So once again, a lot of internode communication bandwidth is required. This I talked about. A query to a web search engine like a Google web search engine will require multiple parallel communication to multiple nodes in the cluster. Each cluster actually hosts an inverted index. This inverted index is what they use to search for your phrase, and then they return the most relevant results. Even when you build a website today, a modern website, even a single page website, okay, to make sure that that single page website loads extremely fast for a client, it actually requires coordination, communication with hundreds of microservices that are running behind the scenes on remote nodes. A lot of data is collected from each of these individual microservices at the backend, collated together, put on a dynamic single web page, and loaded on the web client side. So the reason you see so fast single page websites is because there's a cluster-based architecture at the backend, and which is having a lot of server-server communication. Of course, for the client, it makes the latency going down. But for the data center network, it results in an enormous high volume of server-server traffic. So if you look at data center network and the challenges that exist inside a data center network, then one thing is, yes, the internal traffic is big. And this is what we've been saying. This is what Facebook article said. The external traffic is growing, but that's still a tip of the iceberg. The internal traffic is actually capital BIG. It's big. It's enormous. It's huge. But it's not just the traffic which is the issue over here. From a networking standpoint, okay, that is one requirement for my data center network. I have to handle a lot of server traffic. That becomes a requirement for me when I design my data center. But the other key requirement comes from latency. The deadline for network input output, they are tight, very tight. Look at all these applications. The four examples I took. there is some input-output operations happening on the network in the cluster. We are calling it network I/O. You can see that the latency in this network I/O operation is extremely tight. Why? Because in all of those examples, we realize that there's a client sitting somewhere who doesn't know what your backend architecture is. This guy has sent you a query to the master server. And within a reasonable amount of time, this client expects a response. What that reasonable amount of time? Because that reasonable amount of time is diminishing with our patience. As our patience starts to grow over a period of time, go lower and lower, this time is also becoming shorter and shorter. With network bandwidth coming in hundreds of megabits per second, I having a 200 Mbps broadband connection at home, I expect that as soon as I send a request, I should get an instant response from the server. So these timelines are dependent on the user experience, my user's patience level. And we all know our patience level in this modern era is diminishing. So to have better user experience, this timeline is constantly reducing and becoming shorter and shorter. But a part of this timeline, while we talked about it when we talked about traceroute application, what did we see? A part of this complete timeline. So if I draw this timeline, I say this is when the request goes out from the client to the server. This is when I expect the response coming in from the server. A part of this time will go into what? The round trip time. Right? There's a time that it takes me to send a request over the internet. This request goes over the internet from the client to the server, and then from the server, the response coming back. This was always the case. That's the round trip time. And we saw that transport layer protocols like TCP, they built their entire design of their sliding window and congestion control algorithms on what? They measure on the round trip time. Okay. So on one side, there are so many algorithms which have been built on the network round trip time. On the other side, we are saying, okay, this architecture of the server has evolved. Now this guy is not the one who's going to answer query. To make it faster, I'm actually, because this is a complex query like a financial analysis query or a data analytics query, I'm actually split it amongst multiple servers in a cluster, requesting them to solve a part of the query and give it back to me where I'll consolidate it and give the response back. I'm trying to improve the computation. But what additional effort time is it adding? It's adding this network I/O time. So the remaining part of this time is coming from network I/O. And because it's actually a subset of this overall timeline, you can understand what I mean by this time being tight. There's not a lot of luxury for servers to communicate with each other. There's some millisecond time frame within which they have to do this entire thing together very, very quickly so that the response can go back to the client in time. That's one of the biggest challenge for the data center network beyond the traffic itself. Right? So traffic is one thing, right? Which is basically we are talking in megabits per second throughput. How many Mbps of traffic do I have to handle between my servers? But this is what we are talking of in sub-millisecond time boundary. What is the latency involved or the delay involved in the server-to-server communication? They're two different things. This is throughput and this is latency or delay. There are two things contributing immensely to my data center network design. They're throwing the biggest challenge towards my network design. The third thing we said on the previous slide is where is the bottleneck going to come in? When there's so much of server traffic, the bottleneck is going to come between as a consequence of the server bandwidth. So the data center network is bound to see congestion because of the internal traffic being big. So challenges with congestion and congestion handling exist within a data center network. How do I design my data center network so that there is no congestion, or how do I overcome congestion in my data center? Right? That's where congestion control methods come into picture. TCP introduces a new challenge in cluster-based architectures or MapReduce architectures, which is what we know as TCP incast. Okay. Okay, I'm going to discuss this in the subsequent slides. I think I've discussed already, but yeah, let's go through it. Right. So internal traffic. See, just this slide is only giving you a perspective. I've already said enough about it, but just a perspective. Why do we say the traffic is growing? So if you look at 5 years back in 2020, and then we'll talk about today. See, 5 years back in 2020, this is the amount of traffic that we were seeing over the internet. Every minute, there were more than 1.6 million Google searches being made. Here we are actually all talking about client server traffic. 1.6 million Google searches made every minute. 260 million emails sent. 47,000 apps getting downloaded from these app stores. 220,000 photos uploaded to Facebook every minute. And overall, over the internet, other than what we've just looked at, 660 million data packets were transmitted every minute. This is the volume of traffic that we were observing on the internet. Now, when Facebook says that traffic which is coming to us from the internet is only a tip of the iceberg, this is the traffic they are referring to. This is what it was in 2020. Across the globe, Facebook servers were receiving 220,000 photo uploads every minute. And this is only a tip of the iceberg. Inside, the Facebook servers are exchanging data at a much higher percentage than the just this. And when this was 2020, we are now 2025, 5 years down the road. So what will this figure have become? The estimate has always been that when you look at the global IP traffic, every year it grows 5 times of what you saw in the previous year. So we are 5 years from 2020. This traffic would have grown 25 times. It's like 1 crore plus of photos uploaded per minute across the globe on Facebook, or at least 50 lakh photos if I make it 25 times. 50 lakh plus photos every minute being uploaded from across the globe over the internet. That's the traffic coming into Facebook data center. So that's the incoming traffic. Inside, the traffic is many orders of magnitude even more than that. That is the volume of traffic we are dealing with in a data center. Okay. So this diagram on the right is showing from 2012 to 2015 how the traffic looked like. It's basically dividing the traffic into 3 parts. One is the north-south traffic. What do we mean by north-south? So in data center terminology, the client server traffic. See, when you draw, the way we draw it is we draw a client as this. We say this is the server. And then we go to a distributed server architecture. We make many other servers like this. So actually, this client server traffic is also in networking terminology always called the north-south traffic. Okay. This is what we mean by north-south. Not whenever you see the term north-south traffic, it's denoting the client server traffic. Okay. So the north-south traffic that a data center is getting is the light gray one. This is what is the client server traffic. And this light gray is what we are referring to on the left on the slide. This is what is the traffic being referred to. But compared to this, if I look at the east-west traffic, the east-west traffic is the server-server traffic. Why? Because it's going east to west, right? Across between the servers. So north-south denotes client-server. East-west is a terminology used to denote server-server traffic. Within the data center, the black one is the server-server traffic. Can you see? The server-server traffic is more than 90% of the rest of the traffic. The third one you can right now ignore. It's inter-data center traffic. Traffic that goes from one data center to another data center. It's a smaller percentage of the traffic that's client server. Right? Sometimes you see entire handling is not within a single data center. You have multiple data centers and traffic flows across data centers. That's that third part in between. But even if you ignore that for now, look at just the ratio between the dark gray and the light gray, lightest gray. And you will realize that the east-west traffic, which is the server-server traffic, it accounts for more than 90% of the total data center traffic. So the challenge that a data center network sees is not because of the 220,000 photos that are coming from the internet to Facebook server. The challenge is that more than 90% of this traffic is actually inside the data set, the total traffic. Okay, so really, when you look at these figures, you will realize what is the kind of volume of traffic that data centers like the ones like Facebook and Google or Amazon have. What is the kind of traffic they are dealing with? It's huge. Okay. Then, okay, so network traffic is huge. We've talked about it. Deadlines are tight. That I think we've adequately covered. We'll talk about the issue with congestion, network faults, capacity of the network, and then lastly, we'll talk about this issue which we said about TCP incast. Okay. So when you have a network, like a data center network in this case, which is handling such a high volume of traffic, what is the okay network? Okay, let me first, before I go ahead, let me look at what Pradeep has put on the chat window. What is server-server traffic? It is not the same traffic which is coming from client. Pradeep, were you there all through this class? Because this question put actually disappoints me, to be honest, because adequately, this is what we've been talking of right from the time we started discussing application network dance. And when we talked about how network applications evolved to cluster-based applications, we've been talking about what is server-server traffic. The trigger for the server-server traffic is coming from the client. But while there is one message which comes from a client to a master server triggering the interaction, there are multiple server-server messages that result because of cluster-based application. So this is what we've been talking of since the start of this class. So if you ask me that question, I will really be very disappointed. So anyway, I'll, without spending more time on it, or actually others spending more time on it, I'll just say go through the class again, the recording again, you'll get an answer. Okay, so back to our discussion on data center network challenges. Now we know that when we talked about the internet, we said network faults are always common. You can have a link going down at any point in time. You can have a router or a switch failing at any point in time. So when we talked about distributed routing protocols, we talked about these protocols as if they were dynamic routing protocols, in the sense that they were algorithms that were constantly running dynamically as the network condition changed. A network link went down, a node went down, congestion on a link increased, capacity changed. the routing protocols were dynamically working to adapt to those network conditions. So in a way, we were saying that those routing protocols are intelligent protocols. They are adapting to the changing conditions of the internet. Now, when we look at a data center network, because of the fact that we are okay, one thing that we saw when we saw that Google data center video was the volume of physical servers that existed within a single data center. But that gets bloated many folds because of the virtualization technology. Okay? The number of virtualized machines, server machines, or the number of virtualized network functions which arise as a result of NFV inside a data center, which as I a little while back had distinguished as a cloud data center network, a virtualized set of infrastructure for compute, storage. If each of them is seen as a managed object, as a device, they can independently have faults, they can individually recover from faults, then each of them in management, network management terminology, we call it a managed object. Every entity in a network is considered a managed object. So when you look at a virtualized cloud infrastructure, the number of managed objects that we are dealing with are at least 10 times greater than what we saw before cloud computing became popular in legacy data centers that enterprises used to have in-house. Okay. So what we need today in these modern data centers and the virtual infrastructure that gets created on top of that physical data center is a method to dynamically address so many different managed objects. Okay? So today our networks that are there in the cloud environment, they dynamically perform operations like VM migration. Why? Because a no server fault happened. A physical server goes down. Now, a single physical server could be running 100 virtual machines. When a single physical server fails, all these 100 virtual machines that were running on this physical server, they need to be migrated from this physical server to another physical server. And this is what in cloud terminology, in cloud computing, we call it VM migration. All of it is done dynamically in a cloud environment. As traffic load grows from clients to servers, we need elastic scaling of our backend microservices to handle those traffic surges. So what is happening in our cloud network? Not only are the number of managed objects multiple times more than legacy data center environments, the network itself is very dynamic. VM migrations are happening because of node faults. Applications are scaling to more VMs because of higher traffic surges. All that is happening. Okay? So what do we need in a modern data center network is a intelligent form of operations and maintenance system, a system which can manage network faults dynamically, recover from those network faults. When the network itself is so huge, you need intelligent operations and management systems. Okay. Now, as networks grow, the number of faults that you will observe in the network will also grow. An example it can be seen from LinkedIn provided data. LinkedIn published this data in 2015, where they said that in their networks, in their data center network, they observed that between the time 2010 to 2015, their data center network saw an 18-fold increase in the number of faults. So the relation is directly to the size of the network. As their networks grew, the number of network faults also saw an 18-fold increase. Correct? But as our network boundaries are becoming blurred because we are talking about virtualized environments, virtual networks, it's detecting a network fault and isolating it is becoming more and more difficult. It's not like your physical network where you know which node has failed. Right? Or if one node has failed, that it impacts a handful of people. Here, a server failure impacts hundreds of virtual machines. So, in data center networks today, because of the nature of traffic that they're handling and the kind of applications they are running, they have a dire need for intelligent operations and management and network fault recovery systems. Okay. Uh, so how do we address these network faults and capacity challenges? Capacity challenge I'm skipping because I've already talked enough of it. This is coming from the fact that there's so many heavy load server traffic causing the network congestion. So how do you address these network faults and capacity challenges? There are multiple techniques that modern data center networks use, and these are what we are going to talk about in the following 3 contact sessions after our mid-semester regular exam. Today is more of an introductory discussion about what is a data center network, why is there a challenge. I'm just introducing you to it. But these are the things we'll talk about in the subsequent classes. How do I address these network faults, which are so common in data center networks because of their size? Right? So there is more and more focus, as I said on the previous slide, on intelligent operations and management. So I need to build networks which are self-healing networks. Self-healing means they should be able to detect the fault and recover from it by themselves. Intelligent networks. Okay? Without waiting for a human intervention, for a network administrator to spend hours detecting what is the root cause of the issue and then going fixing it. I need to design networks which are self-healing, properties. Okay? If a fault has happened and if human intervention requires hours to fix it, I don't want the network to be down for those hours. So the network should have self-healing properties. It should be able to recover and start working. While, of course, the network administrator will do his bit. He will try to do a root cause analysis, try to figure out what is the root cause of that problem, go and fix that problem. He will do that. A network administrator has a tremendous role to play in a data center network. In fact, all these data centers that are mushing all around our country and the globe, one of the biggest job market that is coming up is networking engineers, infrastructure engineers. They are the ones who are going to solve these network faults. But it will take them time to solve it. In the meantime, the network should not go down. So I need the network to be operational all the time. I need to build self-healing network. So this is one property that we will see. How is this happening in data center networks? Why are our networks self-healing in nature? This will you will observe when we talk about the topology of data center networks in our next class. Okay. The use of intelligent analysis for network fault prediction, detection, isolation. So humans can no longer work the way they used to in smaller local area networks. As we said, we need intelligent O&M, and this can come in by using the data that we can collect from the network. Okay? And this part of our discussion will actually lead to the topic that we will cover towards sometime between classes 14 to 16, where we will talk about importance of network monitoring and data collection. Why is data center network monitoring important? Why do we need to collect so much of data or statistics from network nodes? Because I can use that data to implement big data algorithms, which help me predict potential faults as they may come in. I'm already saying this part of the network, based on all data analysis, shows that it is vulnerable to failure. Before it fails, I should already address it. I should fix it in the network design. So my network design is becoming more and more intelligent and controlled by intelligent analysis engines that deal with a lot of data collection and using it for predictions. Also, not just for predicting ahead, but also sometimes when the fault happens to detect those faults, to be able to isolate those faults. I use intelligent tools. This is where network monitoring and data collection part of our course will come. Okay. We've already seen that when we brought in software defined networking in an autonomous network, it simplified network operations. Why? Because while dynamic distributed routing algorithms had the benefit that they could operate across autonomous systems, and therefore were very, very useful for the internet kind of environment. They had the shortcoming of slow convergence, sometimes even limitations that led to routing cycles or loops being formed in the network. But as routing computation or flow table computation became centralized with SDN, not only did it mean faster convergence of routing paths in the network, but we saw that by using a generalized flow plus match approach, I could implement traffic flow control intelligently using this whole concept of SDN and SDN control. I could identify flows based on a pattern matching, generalized pattern matching technique. And once the traffic flow was identified, I could act on it using different ways to build a firewall, to build a switch, to build a router, to build a NAT gateway, all of it using SDN and SDN. So the way to address such high capacity networks like the data center network is to do all of this. I'll come to the last point, but build the network using a topology that is self-healing, that has self-healing properties. That's where our discussion on topology will come in. Use intelligent data analytic algorithms that help predict, detect, and isolate network faults. That's where network monitoring and data collection will come in. Use intelligent techniques like SDN and SDN controller so that your network operations can be simplified and lower chances of faults being discovered, cyclic loops being formed in the network. Lastly, the challenge of capacity. How do you handle congestion in the network? By bandwidth over subscription. Okay. What this means is I estimate what is the kind of traffic that will flow through the network, especially through the core layer. So when we talked about the internet, the core layer or the backbone of the internet was the collection of all those internet service providers who were either tier one internet service providers or national internet service providers. They were the backbone of the internet. We called it the core layer of the internet. And we said that that is handling the maximum traffic. It is what keeps the internet alive. If the backbone goes down, the entire internet gets disconnected into smaller sub networks. Same way, we will see when we talk about the topology of the data center network, we'll see that even a data center network has a core layer. And it's handling the bulk of the traffic in the data center network. So for that core layer, the only way to prevent congestion from hitting and capacity challenges from coming in is estimating the volume of traffic that flows through that core layer. Let's say that traffic is X. Okay? X bits per second is what flows through the core layer is your estimate. But then you design it using a concept called bandwidth over subscription, which is you say, okay, I will actually have 2.5x bandwidth provisioned in the core layer so that my network congestion never happens. Now, while on one side, this is a cost. I'm actually oversubscribing bandwidth, means I'm going to be underutilizing network bandwidth when the traffic is lower than what I've estimated. So it's a waste of network bandwidth. But on the flip side, bandwidth oversubscription helps me improve user experience. And we said one of the important things for user experience to be good is for network I/O timelines to remain tight. And for network I/O timelines to remain tight, I need capacity, which means I need zero congestion on the core of the data center network. And therefore, I'm willing to live with bandwidth over subscription. That's one thing you will see across data center networks, a concept being followed. We don't do this so much in the internet. But in data center networks, bandwidth over subscription is a commonly used design principle. Facebook doesn't want its subscribers to be put off because of slow service. Same with Google, same with Amazon. They are rather willing to spend more money, oversubscribe bandwidth on the core layer to provide you good user experience. So these are some of the things that we will talk about during all these remaining 3 classes that we will talk about data center network design. How do I use these techniques to build or solve some of the DCN challenges? Okay, last thing I will talk about today, I think this should be the last slide. Maybe, yeah, just the last few slides. Okay. Before we close today's class, is the specific issue that comes in because of use of TCP in most communication that happens in the IP networks. Right? So we said wherever you need reliability, wherever you're not dealing with the time-sensitive, real-time data, TCP is the protocol to use. So reliability equal to TCP. UDP doesn't give me any reliability. So wherever even in cluster applications, I need reliable communication in MapReduce architectures, TCP is the way to go. Sorry, Hemant, I saw on 1206 you put in some chat. I actually read through it. I saw it more as information for everybody in the class, so I didn't comment on it. But thank you for posting it. If there's a question for me, then let me know. But while I was speaking, I also read it. I thought it was more of a knowledge sharing with the class. So yeah, thank you. Okay, so TCP is the way to go whenever you have to use reliable communication. That's something we've learned in the past. But when you look at a cluster map reduce kind of a communication architecture in a data center network, TCP creates a fresh kind of a challenge, which is called TCP incast. Okay. And this is not just for data center network, but in reality, this pathology that exists in the design of TCP protocol affects any kind of communication pattern where there is many to one communication. Okay. In cluster or map reduce, we know many to one happens when all these reduced servers send the final result from their side to a map server. It becomes a many to one communication. Okay. So what happens in the data center network? Let's say each of these senders are actually the reduced servers, which are working on a part of the problem. And this receiver is actually the master or the map server who had actually distributed subsets of the problem to all the reduced. When these reduced servers have solved their part of the problem, what are they going to do? They are all going to simultaneously send their responses to the map server. So it becomes a many to one communication pattern. Okay. Now, when this happens, you will see that, while all of these servers are connected via their own, I'm saying this is more like what? This is a hub and spoke topology. Or sometimes you also call it a star topology. You've created a star. There's one switch in between, which is connecting all servers together. Now, on these individual links, there is no congestion because they're all sending their responses. But on the link that connects the map server, all of this traffic has to go towards it. So what will happen? TCP will observe congestion on that link. And because of TCP's behavior, what do we know? We learned of AIMD, additive increase, multiplicative decrease. As soon as the response goes from all of these senders, this link will get congested. Response or acknowledgements from the receiver might get lost. Even some of the packets might get lost. TCP will detect congestion. What will it do? Dramatically cut its throughput. Okay? This is what we've learned about TCP. This is a problem which in the many-to-one communication patterns is bound to occur. You will always observe AIMD behavior in such kind of um, uh, topologies or architectures, and this is what we know as TCP incast. Okay, so this problem we will see in all kind of communicating paradigms in which there will be simultaneous response. The distributed processing cannot progress until all parallel threads in a stage have completed. When they complete, they send back their responses to the master, and that causes a congestion on the master link, on the on the distributed, sorry, in the bottleneck link. This is what TCP incast is. So we'll talk about how do you solve this problem as well later at some point in time, or maybe now. Yeah, actually, okay, this slide is capturing it. So let's quickly talk about it. How do you solve a TCP incast problem? So there's no single solution that is well accepted across all data center networks. There are multiple proposed solutions, and the approaches vary from very simple to very complex. So simple solutions propose modifying the TCP parameters using which the algorithm detects congestion. So they say, okay, increase the acknowledgement window, or if an acknowledgement is lost, do not treat it as congestion. If many acknowledgements are lost, then do it. So it's all about some approaches talk about how do you modify TCP parameters or tweak the congestion control algorithm so that in such networks, it doesn't hit us. The other approaches feel that it is not a TCP problem. Okay, they believe it's a problem of the application layer. Why? Because the clustered or MapReduce architecture is more of an application layer architecture. The application is designed to operate in a cluster architecture. So because it's a challenge for the app, due to the application, TCP should not be changed. We should be looking at how can I create optimized application implementation so that the data transfer patterns at the application level are better optimized. They should not be all coming at the same time. So some approaches focus on this. How can I create distributed cluster-based application microservice architectures where application data patterns are optimized? A third group of people believe that this is a networking problem. Congestion in the network should be solved by the network. So they talk about modifying network switches and routers by either having larger buffers so that packet losses don't even happen. Grow the queue sizes in the data center network routers or switches, especially the ones in the core. Or if you remember when we talked about net congestion in the context of TCP, I said there are two types of congestion control. One is network assisted, and the other is what TCP uses, end-to-end congestion control. Network assisted is what we briefly mentioned then, routers and switches sending an explicit congestion notification to the source nodes telling them that the network is congested. So proponents of networking layer solutions, they say congestion is a network layer problem. So you should solve it with switch modification and introducing network assisted congestion control approaches. And then there is also a fourth level of people who say that actually you don't even need to do anything on the application layer, anything on the TCP layer, anything on the network layer. Actually, you can make link layer mechanisms at the Ethernet layer to have something like an Ethernet congestion control and solve it at data link layer itself. So there are multiple approaches. This is a topic of research. Many people have prescribed many different approaches. There are benefits of each approach and shortcomings of each. Application level solutions are the least intrusive, but they require modification of each and every data center application. Every application has to be designed accordingly. Switch and link level solution require changing the data center infrastructure. You have to design different kind of network switches or routers and switches. So this is only possible with hardware upgrades. If you want more capacity queues, then you need to add RAM into those switches and routers. So hardware upgrades are required. And those who believe it's a fundamentally a TCP problem and therefore a transport layer problem, they are actually prescribing solutions which have other shortcomings. So they are prescribing increasing the retransmission timeout. But even in normal conditions, this will reduce the throughput or slow out the communication. Right? So every approach has its shortcoming and every approach has its benefits. There is no single well-known solution that exists today that can completely solve the TCP incast problem in data center network. Okay? So this is one thing I wanted to talk about briefly. Last slide for today, and I'm not going to talk about much about it because these are infrastructure challenges. Okay? So as network, in a course on networks, we are not going to deal with it, but since we are covering the topic of challenges, I'm just making it a note that for infrastructure engineers, even these are challenges to consider in a data center. How do I cool the data center? The Google YouTube video mentioned it. Because there's so much heat being generated by so many servers and networking devices, DC cooling is a big problem. Because there are so many servers getting connected together in the network, how do I do the cabling so that people are not tripping over these cables? There are going to be enormous amount of cables. It's like a Indian Railways network, right? Set up between stations. Every server being a station, and then there are railway lines being the cables. How do you set up this network of cables? It's a big challenge. Especially companies and organizations will deal with this. They are experts at designing network cabling inside a data center. I think that's a challenge. But from our perspective, the only challenge that we will cover in the remaining classes is the network cost. When we said bandwidth over subscription, 2.5x bandwidth over subscription, it's directly contributing to the cost of the network. Okay, it's cost of the infrastructure. So this is all I wanted you to get introduced to today when it comes to data center network. As I said, it was a whole lot of topics starting from why is the traffic pattern different? Why is the application driving this architecture of the network? What are the challenges? But this should give you a good perspective of what are the things to come. When we now talk about topology of data center networks, how they've evolved in subsequent classes. When we now talk about the challenge because of congestion or TCP incast, I think you'll understand more with this introductory session that we've had. Okay, so thank you everyone for joining in. I know we are above time, but if anybody has some quick question about the mid-sem exam, I can answer. Okay, Jyoti has a question. Are PPTs enough for preparation of midterm or do we need to study Bible? So this, Jyoti, I answered in the very first class. For all my courses that I take, I make sure that the PPTs should be enough for students. You are all working professionals. I understand that. You don't have time to go through textbooks. So if you've been very, very sincere in joining classes, going through my PPTs, you made sure you understand all these concepts, then you are all set for the midterm exam. You don't need to go into textbooks. Okay? Syllabus for midterm exam is still last contact session. Pradeep, contact session 7. Okay? Today's class, I'm excluding it. So in the previous semesters, I've actually always kept this introductory class also as part of the midsem course. But this time around, I wasn't sure if we will get that compensatory class, which we actually managed to get. So I wasn't even sure if I'll be able to cover it before the midsem exam. So I excluded it from the midsem syllabus. Okay. So until contact session 7, till NFV, Yeah, Pradeep, till NFE. That is your course. Someone with a what type of question? Questions will be very similar to the pattern that you see in the previous year exam paper, previous semester exam paper. So see that sample paper on the course page on LMS. The pattern will be exactly the same. Okay. I never repeat questions. So it doesn't help you to try to gather previous semester exam papers. It will not help. Every semester I set up a fresh set of questions. Right? So rather than trying to gather historical questions, what's more important is try to understand concepts, read more. But look at one paper, which is the previous semester paper available on the course page of the LMS. That will help you understand the pattern. The pattern will be same. Okay? The questions are new. So spend more time on studying the concepts that we've learned in this course. Okay. So all the best for your midsem exam. Next time, next Sunday, we are not meeting because it's a regular exam for makeup. For midsem. But the week after next, we will meet. Okay? Because the makeup exam has, between the regular and the makeup exam, we also have one class. Okay. So we will meet once after the regular exam for one class, and then you will have the makeup exam. Ratio of numericals to theory, it is more theory. Maybe 1:6 is what I'll say. Same as what you'll see in the pattern on the LMS course page. 1:6 kind of thing. Six, if the 6 question, then maybe one question may be a numerical. At max. That's the max I'm saying. Okay, because all we've seen networks is more theory, more conceptual, fundamental knowledge. I can give you numericals, but then it requires you to remember formulae and all those things, which is not necessary. Okay, all the best, guys, for your midsem exam. Thank you, and I'll meet you the week after next. Thank you. Bye-bye.